by Rakhmankin, and we'll talk about another paper by Rajala, external length and duality. Okay.
Hello everyone. First, I would like to say thanks for the organizers giving me opportunity to show my presentation. I want to keep the traditional about final talks, and my final talks will be quite introductory and simple, and we will get rest a bit after the hard talks. So, firstly, what's the main idea of my talking? I want to use the idea of extremal length and the modulus and duality and use it for extend, for generalize uniformization theorem. So I want to say sorry because I will repeat some basic objects, definition of basic object. I think it's not how to. Yes, right now. So yes, firstly we will talk about human sphere, and let's define by G a family of curves with finite lengths by a dA. I will denote a sign of area on the Riemann sphere, and let me define density on the Riemann sphere. We consider any barrel function from Riemann sphere to 0 infinity, and we will consider this barrel function as a density function. It's we will calculate how expensive to go through this density if we go for one curve from the family, and we will call this density admissible if for every gamma for a curve from our family, the integral on rho over gamma is at least 1. So if we use this definition, we may define extremal length, or 1 divided by extremal length. It's a model. It's smallest energy of overall admissible densities that calculate how far blocked the families of curves. So we define the object. Let's calculate these objects for some simple examples. And our first and most simple. Yes, of course.
Why did you call it energy?
Energy, it's look like energy. I mean, because it's just integral over square. It's almost everywhere else. It's almost like energy. It's not because it's completely the energy. It's because it has.
It's because it's
Yes.
convex function.
Yes.
Nothing that. But in reality, the infinity is actually realized for the derivative of a conformal map, so that actually rho, and then optimal rho is the absolute value of the derivative of a conformal map, so that's the square of it, which is an energy.
Okay, that depends on the definition of the energy.
Thank you very much.
The potential theory and the potential theory is really good.
Okay, can we continue? Yeah, let's calculate in that simple example. We have a rectangle, and let's get gamma 1 by family of curves join the vertical sides, and gamma 2 by family of curves join the joining the horizontal side. And we have a explicit formula for as gamma 1 and gamma 2 is just b divided by a, and a divided by b. And here we have a main idea of all my talks is the duality of this curve. So let's prove it. Firstly, the same, we have rectangles, and let's calculate the upper bounds. We should find some good density. Let's just get a constant density, and let me say that the constant density in R equal to 1 divided by A, and outside R equal to 0, because we don't really care about density out of the rectangle. So let's firstly prove this is admissible easily. Because for all our gamma, the horizontal projection at least A, so we calculate the integral, we have at least 1. Okay, let's calculate the energy in the same way. We just calculate nothing special, and we got an upper bound of our model. So let's do the same thing for lower bounds. Let's say that we have already some admissible density, and for every fixed y, the horizontal segment lies in our family. So we can calculate, and because it's admissible, we can calculate an integral over all x, and it's at least one by the definition. So we may calculate its integral over the y and get this lower bound. So by Cauchy-Schwarz inequality, we may calculate the energy. The full energy got a lower bound, nothing really special. Because of the symmetry, it's also give us a calculation about gamma 2. So let me go back. So what we want to follow from that, as we see, model is somehow calculate how hard to block the curves, the family of curves. And what we know that if our rectangle is really its vertical side is big and horizontal side is small, it's really hard to block these curves because it's too much number of curves and the length of curves is too small. Okay, and the other side, if it's bottleneck, it's easily to block it. Okay, let's go further and for extend this result to all topological rectangle reds, let's prove that our model is conformal invariant. Suppose we have two domains, and let's f be a conformal homomorphism and some family of curves. Then the image of our family have the same model as the just family. So let's prove it. Firstly, because conformal homomorphism is a bijection, we may build a corresponding map between densities. By this formula, it's not completely what we can do on the Riemann sphere, but because of the sum, I put it out of the context because of the sum idea, because projection of the Riemann sphere to the plane is also conformal. We may think about all integrals as the integrals over Euclidean metric. So what we have two different densities, and we want to say that if one density is admissible, then the other density is admissible. Okay, just let's open the by definition. Here we use that it's a conformal map. Absolute value is goes to the product of absolute values of derivatives. So we see this integral are the same over all curves, also the same about energy. So we prove this is conformal invariant. Model is conformal invariant. Okay, if we have that, we can easily and for free extend our duality to the whole topological rectangle. So suppose we have a topological rectangle with some domain homomorphic square and with four distinguished boundary arcs. So maybe I think a bit about that definition. Maybe I should add something about the boundary. Maybe I should that it's a Jordan bound, have a Jordan boundary. Without that, as I see, the Riemann theorem about mapping that doesn't work. But if I add here Jordan properties that boundaries is Jordan gave, it's enough. Okay.
Sorry, but not only for Jordan boundary.
It's not only for Jordan boundary, but I'm not really professional in that. I think that is it true or not, because it's some tricky mode.
Basically, in the Jordan boundary, it also comes with the characteristic extension. That the conformal map has a homomorphic extension. So that you can basically identify this J1, J2, J3, J4 with the boundary of the rectangles.
Yes, but that's what I want. That's exactly what I want to have. So yes, if so, if I have a Riemann mapping I should have a conformal map, but the tricky moment for me was about the boundary arcs. That's if I have it for free, that's perfect. Yes, if we have so, and because of the conformal invariance about models, so we have a duality for all simple connected families. Okay, but not only for simple connected. Also, let me share another example of duality. Suppose we have an ambos, as just we have a one, this and another one, and we cut out one from another one. And so let's consider two families. First family is a connection family. It's a family of curves that connect one boundary to another. And the other one is curves that separate these two boundaries. These two families. And I also want to prove that in that example, we also have a duality. So let's prove it. Let's prove this explicit formulas. And I do it only from one side, from upper bound, because from other side is completely the same as in situation rectangle. So we want to prove right now upper bound. For proving upper bound, we should find some density. Let's choose a radial density with that adding. So let's prove that person is admissible, of course. And also, let's calculate the energy. For doing this, let's use polar coordinates. So we got the upper bound for model of gamma. Lower bounds get the same as in a rectangle case, because we know that all such curves lies in gamma. And we have a lower bound. Okay, let's do the same for lambda curves. Okay, of course we can consider such density, do the same calculation, and got 1 divided by model gamma as upper bound, and the same because our and should contain all such curves. We have a lower bound. Okay, let's go further. That's the first example of duality between families, between connected families and separated families. And also I will extend it for a higher dimension at the end of the talk. So we define a basic object. We prove something for situation when we have conformal instruments, but what's going on if we want to use this instrument, but we don't have a Riemann structure on our sphere? We want to extend this idea to the metric sphere. Okay, metric sphere is just a metric space which topologically homomorphic to Riemann sphere. I mean, here maybe we just put a S1 topology to the same as a sphere. So let's denote by S square is just two-dimensional Hausdorff measure associated with our metric. And also let's firstly consider a good spheres. The good spheres in my definition will have two properties. That's the first one, as I will call the sphere a two regular if there exists some constant. As all balls have a Hausdorff measure measurable with their square. As it's almost have the same as a sphere in a countable in a quantity way. Okay, elsewhere we want to avoid some bad situation. We want to avoid bottlenecks, and we want to avoid high shifts. So I will call a sphere linear locally connected, or LCC. Further, I will call it LLC. If and only if there is some lambda such that we avoid two situations. First situation, we may think that suppose we have a circle and we cut out some compact, for example, we cut out some path, and let's choose these 2 points. These 2 points align into some poles, but it's hard to get a path between them because we should go out of this path. This is what's going on, what we want to avoid in the first property, and the second property we want to avoid such situation. We have two poles which cut with 1 point, and for given path from 1x to y, we should go through the sum that. Without it, it's impossible. I want to avoid this situation too. And for these spheres, we may consider a great generalization of differentiation theorem. Firstly, I want to define a quasi-symmetric homomorphism called quasi-symmetric if we may control distance of all sorts of all triples of points, as the distance between the 3 points are controlled by some function. And for that, we have a first generalization of uniformization theorem. This is just a well-known theorem of Riemann. So if our sphere two regular in sense that I already mentioned, and have these 2 properties, that mean not have that situation and that situation, and we have a quasi-symmetric homomorphism, quasi-symmetric parameterization of our sphere. But let's go further, and what happens if we want these 2 situations? What we can reach?
Yes.
Our initial domain. What was our initial domain? You mentioned that we don't want these 2 situations. My question is about our initial domain. Was any curves or
Our initial domain is just a metric sphere.
Oh, okay, it's sphere.
It's sphere. It's complete a sphere. When I'm cut this, I mean, this is 2 spheres. We can just add it to each other. It's also, I mean, of course, it's not the same. I just want to say that it's no bottlenecks. Here it's completely what we can have on a sphere because we have our own metric.
I mean, but okay.
We have what's the difference because it's not a Riemann metric. It's one. And we may, for example, collapse some compact to 1 point, or we may say that all points have a zero distance from other kind of.
Yeah, so it's there is a situation when we have intersecting circles, and it's okay. I mean, can we draw the situation when we have intersecting circles, but these 2 conditions are avoided?
Sorry,
Okay, I think I don't get what the domain should look like.
We don't get what, sorry. What's going on here? Yes, what you want to avoid? Yes, what's this?
I want to understand how restricting are those 2 conditions together. I mean, what we can end up with. Maybe give me some example of a situation when those 2.
An example of this would be something that we didn't mention about the past.
Yeah, for example, yes, as I see. Okay, let me think a bit of. I got your question. As I understand, these 2 examples is not completely on the sphere, as it's kind of out of. What's if we want to use this example exactly? Yes.
I mean, like my question, I asked for some example that shows that those 2 conditions are avoided, and we end up with something that is not very trivial.
Okay. Sorry, I'm a bit stuck. What we want to get? For example, what we want to get that it's kind of let's get two spheres and let's put this point as kind of infinite. For example, and as I understand, it's almost here this situation, and all pass from this sphere to that sphere. It's almost goes to infinite somehow. And let's add some. I don't know.
Okay, and that is why we don't have a ball that.
Yes,
Pass
that's
those.
that's example of what we want.
Okay, I guess, okay, I think it's okay, that one.
And what's for that situation? I think what we want I think that situation is it's almost let me think a bit. Okay, let's add this to it's also a kind of infinite.
Okay, so, okay, thank you. No, sorry, no.
And right now it's distance to big
Yeah,
plus in both in the topological way it's okay.
I have a question for the next slide.
Of course.
Next.
But this one?
No, next one.
This one.
Formulation of the theory. So essentially, you already have the homeomorphism between your X and C hat.
Yes.
And what you want to say that it's became quasi.
Yes.
Even only.
Yes.
Okay.
Exactly.
Is
There
it,
exists.
there is, not the same one.
Not the same, but at least one homeomorphism.
Yes, at least one should be.
There is.
Not
Yes, that's how I define the metric sphere. That's how I define the metric sphere in topological space.
But that was my, so it doesn't. Exactly the quasi-symmetry here.
Yes.
Again, if you have.
Yes, exactly. Yes. Okay, yes, what we have, that's I already say, we want to have this situation, and what we, how good parameterization we can find. Okay, let's define another object, metric surface, it's also a metric space, that have such that every point has a neighborhood morphic to the open disk. So for that, we also may define the model. That's a great property of the model that we don't need to have a complex structure. We may use a Hausdorff measure here. And the admissible density defined absolutely the same as in previous case. Sure. And now I want to define the quasi-conformal map in that metric case. So in normal case, it's defined like that. I think I should put here not homeomorphism, but diffeomorphism.
That's smooth homeomorphism.
Yes, of course. Yes, that's smooth. Yes, you're right. Completely right. Yes, suppose you have two planar domains and F is diffeomorphism, and the model's definition that I will have upper completely the same as analytic condition of quasi-conformality. Quasi-conformality. Sorry for that. Okay. The definition that we should have an upper and lower boundary of images of all family of curves. Okay, let's give an other definition. It's a property of surface for all topological rectangle. If our product of dual families, of models of dual families, if we have a lower and upper bound for all these curves, we will call this sphere, this surface, as a reciprocity. reciprocity sphere or reciprocity surface.
Essentially, it's a topological circle with 4 points, 4 mark points. Yes.
Yes.
It's topological.
Yes, exactly. Yes. For that definition, we have another theorem that's proved by Rajala in 9 years ago. It says that if we have a finite Hausdorff metric sphere, then X have a quasi-conformal parameterization when and only when that X has that property. That's also extension generalization of uniformization theorem. And let's
Finally, mean that this has finite measure.
yes, exactly. Finite Hausdorff tool. Of course.
I think there's some nice criterion of reciprocity condition.
Yes, there is at least one, and I will show it. Maybe I will show it right now. For example, this one is if it satisfies to regularity. If we have all balls not longer than r squared, there is a quasi-conformal homomorphism, and that's point 2 is the same as the Rajala theorem that I already showed. This is one criteria, geometric criteria for the theorem. To be fair, that's only one that I know. Okay, let's go back and let's prove some simple ways why quasi-conformals should imply reciprocity. Suppose we have a quasi-conformal parameterization of our sphere in model sense, of course, and suppose we have some topological rectangle. Of course, the preimage is also topological rectangle. So the preimages of all families of curves in the Riemann sphere has a duality. So, and quasi-conformally gives us such inequality by definition. Or we may multiply this inequality on each other, and this product will tense these two models after multiplication. This product of two models are equal to 1. Because of the duality on a Riemann sphere, and we have a reciprocity property. On the other side, it's the key idea of theorem. So I don't want to spend a lot of time to prove it. So okay, we prove something, but not every time we have a homeomorphism, and what we may get in that situation. For example, if I have a sphere and I just get some compact and collapse it into one point. And right now, it's not a homeomorphism because it's not an injective. And but also we want to have a parameterization in that case. What we might have we can reach. Let me define a big parameterization. Big parameterization is a map. If it's continuous, surjective, we not ask for f to be injective, and for all preimage of all points, it must be connected. And we want to follow that inequality. That's our f cannot make all curves too hard, too simple to block. It's our f cannot make our curves to be too simple to block. So in that case, we have a really great theorem that says that if we have a metric sphere with finite Hausdorff measure, then there exists a weakly parameterization which is quasi-conformal, and we don't ask any other restriction on that sphere. So Moreover, this constant is the smallest. As we already know, it's quasi-conformal. It's weak quasi-conformal map is quasi-conformal map when and only when it's x satisfies the reciprocity condition, and this is criteria, the geometric criteria for that. And as we already know, if also x is LLC, then it's quasi-symmetric. So yes, we reach the.
So just to clarify, so upper regularity gives you reciprocity.
Yes, exactly. For example, what's going on when I collapse a disk into one point? There is a shortcut for my curves to go through it. For example, if I collapse this to one point, now all curves, this part is not countable for integral, and it's easier so curves go through it and harder to block it. That means model must be increased, and that's the reason why we not ask here to upper bound. It's lower bound we get everywhere, every time, but upper bound it's not true because of that bad situation.
So like in the weak quasi-conformality definition, that can be defined in the planar setting also, or domains in complex plane.
Sorry.
So we can define weak quasi-conformality for domains in
Yes.
complex plane.
Yes.
Can you give an example which is weak quasi-conformal but not quasi-conformal?
Weak quasi-conformal is given if the R is there and then the weaker split.
No, that is not.
Is it-
That's not my question.
This is an example when we suppose we on a sphere you have a disk which has some compact and you collapse it into one point, and in that situation for the reciprocity condition you should have that the upper bound for a model for the image of the model, but right now the model can be too big because when you collapse it, it's too easy to go through it, and because of that, model is increased stride. It's become a really big. That's the example. Sorry.
Yeah, that I understood. But my question is different because
Mhm.
the example that you gave is in the metric surface setting, and there you can collapsing point works. But I'm asking whether there is any weak quasi-conformal map between domains in the complex plane which is not quasi-conformal. Does there exist any weakly quasi-conformal map between domains in the complex plane? Because once you have a domain in the complex plane, you cannot apply this trick of collapsing.
Okay, I got it. I think no, but let me understand. Is it?
I don't know.
I think what we if we have x, it's a Riemann sphere. Yes, you ask what's going on if x is a Riemann sphere. But for a Riemann sphere, we already have a uniformization theorem.
No. Maybe I will ask.
Why is this not example equals not true?
No, because my question is different.
That's a mapping duality, right? You take a mapping, it's not a it's not a one-to-one mapping, it's a function, right? It's supposed to be surjective onto the domain and
What is the domain?
the domain is like the plane you take a disk collapse to a point, and everything else is identity or something.
So plane collapsing to a point.
It's
But then that's not-
it's continuous, right? Think of, or it's not.
So in this example, what is X?
What is x?
Yeah.
X is just our sphere. When we
Sphere?
yes, magic sphere.
Well, like, in this example, what is the proper mathematical definition of X in this example?
It's this example. What you have? What should we have for define a metric? We should we should put 2 points and calculate the distance between them. How to calculate the distance between them if we collapse a disk into 1 point?
Yeah.
Or let's calculate the smallest path, and if go through the disk, let's cut it out of the and distance between these 2 points becomes smaller. That's it.
Yeah, so,
And for that, let me
so you are saying that every weekly quasi-conformal map from sphere onto sphere is quasi-conformal,
No.
no?
no, no.
And this is the example.
Yeah.
This is
Collapsing is not fast.
yes, because firstly it's not injected.
Not injected. But weekly quasi-conformal doesn't have to be injected.
Yes,
Yeah,
that's what we said. One
So like,
integration.
yeah, so like take the whole this and collapse it to a point in the image.
but that doesn't remain a sphere itself.
Why?
not?
Why not? It's a logic sphere. It's not. It's not a limit.
I mean, like, let's define the function to be, let's say, the distance from like a point. You just like radially shrink it so that the whole thing goes outside, then that they all thing to a point. It's continuous, right?
Yes, absolutely continuous.
Okay.
True. Okay. So yes, we reached our first aim. That's generalization. Also, if the set of questions is empty right now, we can go a bit further and extend the anomalous example, because I promise that I give the same duality for a higher dimension. Let's also define some new objects, k-dimensional surface. It's such surface that all points, almost all points, lie into some image of some Lipschitz function. It's just, it's almost all points are union of images of some Lipschitz function. So we may define integral over k-dimensional surface in that way, which just have integral over our rho using a Hausdorff measure. Okay, and also can define a model on the family of k-dimensional surfaces, and we can define admissible density on that on almost the same way. But here I want to add the parameter p for gets the difference between dimensions. Sure, and in that case, we have another example of duality, more general. Suppose we have a two-bounded domain, one bounded domain, and in that bounded domain, two disjoint compact sets, and this triple we called condenser, and first set is curves which join into part of this condenser, and the lambda is a family of surfaces that separate them. As an example, it's quite clear. Of course, you suppose we have two spheres somewhere in R3, and this is an element of gamma, and this is the element of lambda. And so, and we also have a duality here. For high-pressure surfaces, it's really important because what's going on if we put here not n-1 but n-k, it's open hash right now. Also, we consider, but here we have a duality, and also this is a great example. What about? We have another 5 minutes. Okay, maybe 2. Okay, I want let's add just one another sentence that's in one-dimensional and n-1 dimensional. We already know the duality, but for the more complex way, if we have a k-dimensional and then minus k-dimensional surfaces, in that case, it's open question. We have that inequality, but we still don't know is it true or not. But I'm not really professional at that because, and maybe that's it. Do you have any question?
Oh, she's sleeping, can't you?
What?
The child is sleeping. Not out, so.
Oh, sorry.
Maybe I will again ask, because I'm unable to convince myself. So, since this is happening because it has a boundary. Okay, let us.
Why it's happening?
So suppose we have a proper domain in the complex plane. Take a domain omega 1 and omega 2. Take a map which is deeply quasi form. We can define because that doesn't depend upon whether it's a C hat or something. Between two domains, whether there is an example of a deeply quasi form map which is not possible.
So take omega to be the plane,
Sorry.
take omega to be the plane. Yeah,
Okay.
take the function to be defined on the open unit disk
Uh-huh.
is equal to 0.
Okay.
Outside of the unit disk, take a point z and define f of z equal z divided by the distance of z from the disk.
Okay, understood. Okay.
Yes, so that going,
No.
does that not go? Yeah, maybe
No.
something that goes, yeah, it goes to 0, right? If as you approach to 0, you go to 0. After you approach to the disk, multiply, not divide, sorry, multiplied by the distance.
Okay.
Z times the distance to the boundary.
What is the boundary?
You have the boundary, which is the unit circle. Inside the disk, you put it 0. Outside, you just multiply by the distance to the disk.
It should.
Okay.
So it maps everything outside of the disk to the punctured plane, and the disk goes to the function.
Okay.
That's continuous. And I think it satisfies the equality.
Yes. Yes.
Some sort of homology.
No, it does not. It does
How is it
not
possible?
give to the, it does not take everything to the function.
Yeah.
Not everything. What happens?
So I mean, so your function is from C to C, complex plane on complex plane. And you're defining that outside the disk goes to the punctured plane.
Outside, yeah, but then it continues continuously to the whole plane. Outside of the disk, it is defined the identity times distance to the unit circle.
Okay.
Okay, you say that
Maybe you can write
Some-
z times the distance to the circle from z times distance from z to the unit circle. Yeah, that's the formula outside of the disk. And then inside the disk, it's just 0.
That's just models at -1, no?
So I think, let me also,
no.
for B continuous, it's,
Distance between z and the distance.
we don't really need to, it's also possible, but we don't really, sorry, my bad.
Which is,
Yeah,
z times models in ours.
Yeah.
Yes.
I think if we just collapse it, not to multiply to distance, or just everywhere it's just z outside and 0 if oh yes, you're right, yes. Yes, yes, completely.
This one looks good.
You're right. So this is a continuous formula of just doing this. And in that case, of course, it's not injective. And we may increase model of some curves really significantly. That's the key idea. We may consider curves gamma, and this is gamma is difference. And let's cut this gamma to the distance, and this mod of gamma is turns to infinite. That's the problem. That's what we have in that situation. In normal situation, for quasi-conformal, we should have a reciprocity. A reciprocity says that have a boundary for the, where is it? Yes, and so, for quasi-conformals. It's quasi-conformal. For quasi-conformal definition, we have a upper bound for the model of for the image of the family. But in that case, we don't have an upper bound.
But the complex plane is reciprocal. Oh. Yeah, I mean, please.
But then not, it's not the home.
Yes, what we want to add that what we want to have the parameterization in case we don't have a home.
Let's talk later, because we have another thing coming up. Let's thank.